Welcome back to the lecture.
Now let us look at this question. So what choice of Q would make the elbow tight? What do you mean by making the elbow tight? The lower bound that we have becomes equal to the likelihood function, right? What value of QZ would do that? Any guesses? What should be the density function that this Q should assume for this particular expectation be equal to this particular log of that expectation? Let us look at that. It is only algebra. Let us do that algebra and see what value, what choice of this QZ, okay, should make this tight. Okay, so why are we even asking this question? Now suppose you want to optimize, get the model parameters theta by solving this problem. You know that f theta of Q, okay, also depends on choice of Q. Now you choose a Q, you get a lower bound on the likelihood function. Now suppose you want to maximize a function and you are constructing a lower bound and optimizing that instead. What do you want your lower bound to be? You want your lower bound to be as close to the actual function as possible. Now the question that you are asking is, what should be the choice of Q that I would have such that the lower bound that I am constructing, because I cannot optimize the original function, is as close to the original function as possible. That is the question that we are asking. Now in the most general case, this optimization problem can actually be slated as two optimization problems, okay, one over Q and one over theta. Okay, what are we doing here? We first optimize, or we first construct the lower bound, okay, and try to make it as tight as possible by finding a function Q. Once we construct the lower bound, we find the parameters that would maximize the lower bound. You understand? Now look at this. We will not do it in this course, we will do it in the next course, but I will just tell you for the sake of completeness. Look at this. If you were to optimize this with respect to Q, okay, you are optimizing with respect to a function. See, optimization with respect to theta is an optimization over variables. Optimization over Q is an optimization over functional space. Do we know how to differentiate or optimize over function space? We do not, unless you have studied variational calculus, and that is why these methods are also called variational inference methods. That is why they name variational autoencoder, right. Again I will start the next course from VAE, right. I will tell you why EM is broken and you will have to move away from VAE, this thing and all that, but yeah. So if you want to optimize over Q, then you will have to optimize over function spaces. But here thankfully, no, we will see, we will not optimize over Q, but we will ask this question and we will try to find out what Q would make my bound tight, and not explicitly solve an optimization problem over Q, as we will see now. Is this clear? Okay. So now let us try to answer this question, what choice of QZ would make the elbow tight, in the sense that if I have to solve this optimization problem, then what is the value of, what should be the functional form of Q such that this is maximized, f theta is maximized. What is the maximum value of f theta of Q? It is L theta. The maximum value of f theta of Q is L theta. So what value of I should not be saying value, what functional form of Q would make f theta of Q equal to L theta is what we will ask. Question?
Why do we want the elbow tight? It still doesn't make sense, because if it is not tight, then we have space between the L theta and the maximum of this. Isn't that space good, because that makes the likelihood even more? Tightening it to the lower bound is...
No, we see we are not pushing down the likelihood, we are pushing the lower bound up to the likelihood. See, what happens is, if you maximize the likelihood, I mean I will write the diagram later when I complete the EM, but if you are maximizing this lower bound at every point, right, this gap, your parameter may not cover this gap, this is a bad thing. So you don't have any control over likelihood, that is there. All you have control over is your lower bound. So pushing the lower bound as close to the likelihood function as possible is a good thing. You don't want that gap precisely, right? I want the parameters that would lower this gap. Okay, I will write the diagram in a while. Okay, it will be much clearer. Okay, so let us look at this. What choice of QZ would make the elbow tight? So let us look at, let us consider the difference between, I just mentioned that the maximum value of the elbow is L theta. So let us look at what is that gap that he mentioned. So consider this L theta minus F theta of Q. So what is this gap? This gap is log P theta of x minus that expectation, which is QZ, what is that term, log P theta of x and z. Log P theta x z divided by QZ, right? This is what it is. This is equal to, I will skip the algebra, log P theta of x minus, maybe I will write it. So this is at least one step, QZ log, I will write the joint distribution as the product of marginal and conditional, okay, divided by QZ, alright. So I can take the marginal over x outside, correct, because it is independent of z. Is this alright? What did I do? So I just took this log P theta outside the summation because it is independent of z, right? The marginal of x is independent of z. I just took it out and these two terms will get cancelled off, and what I have is this particular term, which is QZ log QZ divided by P theta of z given x, right? What is this term? Do you recognize this? This is the KL divergence between Q and P theta of z given x. So what was our LHS? The LHS is the difference between the likelihood and the lower bound, correct? Now we already saw that because it is a lower bound, the maximum value of this lower bound is equal to the likelihood function, okay. Max of f theta of q is equal to L theta by definition, or by construction, I would say, not definition, actually definition, but yeah, I can say by construction. Which can have, therefore L theta minus f theta of q, this can be 0, okay, only if the KL divergence between QZ and P theta of z given x is 0, which implies the optimal choice of QZ that would make the elbow tight is the posterior of the latent variable given data. Right. So if you can make, if you can choose your density over z as the posterior, see please note that this density, right, the posterior of z given x is also a density on z, right. We started by saying qz is any density on z and p theta of z given x is a density on z. So if you choose your density on the latent variable, the marginal on the latent variable to be equal to the posterior of z given x, then the lower bound that we constructed on the evidence or the log likelihood will be exactly equal to the log likelihood. Okay. Why is this result important? Let us go back to what we wanted. We wanted to maximize the likelihood function. We could not maximize the likelihood function, therefore we constructed a lower bound on it, and that lower bound depended on another function, another density on q, and we wanted to first make the lower bound tight and then optimize over the parameters. Now we just found out that the best value that we can choose, or just best function that we can choose on q, is the posterior of z given x. Now suppose in a model, okay, you can estimate p theta of z given x, then you do not have to solve this optimization problem over q. You can just compute p theta of z given x and solve an optimization problem over theta, that is it. Okay. And for those latent variable models in which case p theta of z given x is not tractable, you will have to first solve an optimization problem over q using variational methods and then construct a lower bound and then optimize over the parameters. So in models such as let us say diffusion models and VAEs, the latter approach is taken where estimating p theta of z given x is not possible. But in the cases of mixture densities such as Gaussian mixture densities, we will see that we can estimate p theta of z given x, and since we can estimate p theta of z given x, we do not solve this optimization problem over q, but we will compute q to be p theta of z given x and optimize over theta, that is it. Does it make sense? So what are we doing? We have an objective function that we would want to optimize with respect to parameters theta, we can't do that. So we constructed a lower bound on it, and the lower bound is constructed in such a way that for that particular value of theta the lower bound is tight, and then we optimize over theta. Now note this, suppose I change my theta, the lower bound also changes. Okay, remember this, because what we actually end up doing is we will iteratively optimize over theta and q, in the sense that we start with a theta, okay, and find my q to be p theta of z given x. With that as my q, I will optimize for theta. Now my theta changed, because my theta changed, I will have to construct the new lower bound, and with that new lower bound I push my theta further, and I keep doing this iteratively, and this is the EM algorithm. Let us write, why is it correct? Is that the question?
Why will it result in a solution? Because we are changing.
We will see that. We will see that. Okay, so an iterative algorithm initialized with some theta naught, okay, compute p theta t, or rather compute qz qt of z to be p theta t z given x. I have to write a for loop here, no, for, hold on, for for t equal to 1 to convergence, do compute qt to be equal to p theta t of z given x, right? Yeah. See, there is this counting from 0 versus counting from 1 issue that I always get into because I am trained as an electrical engineer, right? So we count from 1. For t equal to 1 to convergence to compute this. Okay, so once you compute this, estimate the lower bound, estimate f theta t of qt to be equal to expectation of, this is over q t of z, log of p theta t So this can be computed. Why? Because we already know what p theta of z given x. We know what qt of z is. Are you all following what I am saying? Right? Since we know what qt of z is, we can compute this, and since we know this, this entire expectation can be computed. So once you do this, what do you do? Estimate theta t plus 1 to be the maximum of or theta. So this should be theta, not, yeah, it's a function of theta. So we have qt that we fix. See, somebody asked a question, right? Why don't you make this a function of theta? It's actually a function of theta because you see this is qt is p theta t, and because it is computed at theta t, this qz becomes a function of t as well, but it just makes the notations a little complicated. That's why I don't put theta there, theta t again there, okay, right? So now find theta t plus 1 as the one that maximizes this ELBO computed at that qt, okay, and then replace that's it. I don't have to do it. This is all. So you are iterating over it. You understood? So start with an assumption on theta, okay, and then compute the q to be p theta t at that particular theta z given x. Compute the lower bound and maximize the lower bound with respect to theta, and keep repeating this. Come again? Here you mean? No, it is p theta. So you compute this as a function of theta. So what you fix is q, because this entire thing has to become a function of theta, right? So this, I'll maybe write it as f theta at qt. So you have to construct,
His question is to with respect to which theta? Theta t minus 1 or which t? Theta at which t? What is the index?
This is theta t only. See, that's why, see, when I say qt already has theta t in it. Qt already has theta t in it. The posterior that you compute is with respect to theta t, right? So this entire thing now will be using theta t, but will be a function of theta, right? Is okay. So this is exactly what the expectation maximization algorithm is. Okay, this step is called the expectation step. And this is the maximization step. So now before you ask questions, just stare at the algorithm first, understand the algorithm. I wrote theta 1, no? said that electrical engineering problem. So I started with theta 0, then I initialized theta 1. I realized that quickly. Okay, so please look at the algorithm and try to understand what it is. Two things have to be done now. I'll have to show you why this algorithm is correct. So what we are doing is constructing a lower bound, making it tight and maximizing it with respect to theta and doing it iteratively. Why should this algorithm work? I will show this in the next class. Okay. The other thing that is to be done is I will have to apply this algorithm to GMM. Okay, and show that how the algebra works out for the case of GMM. We will do both that in the next class. However, please note this, there are two important observations to be made here. One, EM algorithm or rather variational inference, this is also called variational estimation methods, they will take this particular form only if we can compute p theta of z given x. For only those models, okay, for which we can compute p theta of z given x, we can apply an iterative algorithm such as EM. This is very important because in this course we will only look at GMMs, which are the case of latent variable models for which p theta of z given x is tractable, can be computed. And for the cases where p theta of z given x is not computable, then you need to estimate q also within this. See, why am I saying this is for the sake of completeness? Because initially when I introduced latent variable models, one of the questions was we do not even know what z is. How do we deal with it? We deal with it by estimating a distribution over z, okay, using variational methods along with the model parameter estimation, which boils down to estimating q. So that is why in the most general form you estimate you write ELBO optimization as an optimization over both the model parameters theta, and by the way this q is called variational distribution. This q of z is called the variational distribution over latent variables. So you optimize over the model parameters and also the variational distribution. But in the cases, okay, where the variational distribution is tractable, we know that the optimal variational distribution is always the posterior of latent given data, always, because that is algebra. However, for some models like VAEs, this posterior of the variation distribution over conditioned on data cannot be computed, and that is when we resort to estimating that explicitly as well. But for this particular course and the particular case of a mixed density, the posterior of the latent variable given data can be estimated, and that is why we resort to this iterative algorithm where we initialize some values for the parameters. Remember, in the case of GMM, what these parameters are? Alphas and mu's and sigmas. We initialize them to some value and we compute the posterior of the latent given data, and then we compute the lower bound and we optimize the lower bound with respect to theta and we iterate, that is it. And once we get the new theta, that becomes you again compute the posterior of the latent given data, compute the new lower bound and keep iterating over it. I will have to still answer two questions, right? Why this algorithm is correct? So what we will show in the next class is that I may just make the statement and then we will stop. We will show that EM guarantees that the likelihood that you estimate, likelihood that you get at theta t plus 1 is at least equal to the likelihood that you get at theta t. Please see this, it is not saying that it is strictly greater. This algorithm will ensure that the likelihood will never decrease. Somebody was asking, GMM is a universal approximator, right? EM algorithm is there, ML should end here. It does not end because this is not a strict upper bound. This will show, next class we will start by showing this, that if you run the EM algorithm will ensure that the likelihood never decreases. And also I will work, at least I will show the sketch of the algebra for the case of GMM, and then we will continue with the base classifier estimation. Please again remember the story. The story is that we want to estimate the posterior of y given x in the case of supervised modeling, and to estimate that we want to estimate the class conditional densities, and class conditional densities may be GMMs. That is the storyline so far. give an example where p theta of z given x cannot be computed, is it? Neural network, variational autoencoders. If you make your p theta of x given z not a Gaussian but a neural network, then p theta of z given x cannot be computed. Ask me this question next class. When I define p theta of x given z for the case of GMM, I will show you the case where it cannot be computed. Come again?
What's the stopping condition for
Good question. What is the stopping criteria for this? I'll tell you next class. Okay. So thanks for attending this class, and next class we'll continue from the correctness of EM and then look at EM for GMM. Thank you.